We have our final presentation. So I'd like to welcome Suzanne Witt. She's the Research Director at Enspired Solutions.
All right, thanks. Yeah, thanks for everybody sticking around for the caboose of the conference. Yeah, I'm Suzanne Witt. I'm Research Director of Enspired Solutions. So we are a women-owned and women-led startup company out of East Lansing, Michigan. And I'm going to be telling you about our reductive defluorination technology for PFAS destruction. So why we're interested in PFAS destruction is because some of these PFAS and capture and disposal remediation methods leave this lingering liability because we can take PFAS out of the water, but then the question is, what do we do with that sorbent media or membrane reject concentrate? And oftentimes it gets re-released into the environment when we dispose of that. So what we want to move towards is to PFAS destruction to get away from that closed cycle of PFAS capture and re-release. So if we destroy the PFAS in the water, then we can lead to a non-toxic discharge. So the technology that we are working on at Enspired Solutions is called micelle accelerated photoactivated reductive defluorination, or just PRD. And I don't think it's as well known as some other destructive technologies, so I'm really excited for the chance to describe it to you. So in the first panel here, if we have PFAS suspended in water, so all these little blue dots are a PFAS molecule, we add a reagent that is a surfactant, and that helps PFAS form these micelle structures, which we call a reactive cage. Our second reagent is an electron donor. So that also likes to associate with the micelle, and that electron donor can be UV light activated. And when we shine light on it, it releases a hydrated electron, which can then, it has sufficient energy to break the carbon fluorine bonds of PFAS molecules. So that results in free fluoride ion, water, and simple non-fluorinated carbon compounds. The micelle structure here is really important for the efficiency of this process because it takes PFAS and water and packs it into this nice little structure that our reagent also likes to associate with, so that electron transfer can happen very rapidly. The data that I'm going to show to you today is dealing with benchtop treatability testing that we have conducted on a variety of different water samples under a DoD-sponsored project. So this is a picture of our setup in the lab. So each of these columns can hold 300 milliliters of solution. So we put our PFAS contaminated solution in there along with our reagents, and these glowing blue things are our UV lamps that we stick in there. And so we stir the reaction mixture while irradiating the solution. And what we do is we measure fluoride production by ion selective electrode in real time as the reaction is progressing. And that's just a very quick, cheap, and easy way for us to show that the reaction is moving forward, right? So I can, screen samples very rapidly, and I don't have to send every sample off for PFAS analysis. So just to give you a little bit more insight into how the reductive defluorination reaction works, this is our standard reaction that we run, which is a sample of DI water that's spiked with 1.25 part per million PFOA. And so that's this sort of teal or aqua colored bar here. And as we shine light on the solution with our reagents in there, we start to see a decrease in the PFOA concentration. Meanwhile, in the pink, we start to see an increase in the fluoride ion concentration. So at this first point, we're at 31% defluorination. So 31% of the fluorine that was previously bound to PFOA has been released as fluoride. And that corresponds to over 99% PFOA degradation. And we have some of the shorter chain compounds coming up. So this reductive defluorination reaction breaks down the carbon fluorine chain linearly. So if you start with a C8 compound, you go to C7, C6, C5, C4, and eventually we get to those simple non-fluorinated carbon compounds. As we continue to irradiate the solution, we release more fluoride. So at this point, we're at 64% defluorination, 3 orders of magnitude PFOA degradation. And we see that some of the shorter chain compounds are releasing fluoride now too. The hollow bars here are non-detect values. So at this second point, we are non-detect in the C7 compound. And as we keep going, eventually we become non-detect in all the shorter chain compounds aside for PFBA. So we're at 92% defluorination at this point. So that remaining 8% is due to that little bit of PFBA that's left over. If we were to continue irradiating the solution, we would see that coming down too. As you can see, the PFBA concentration is decreasing as the reaction progresses as well. Okay, so now I'm going to go through some real world water samples that we have treated as a part of this DoD project. And the first is a groundwater sample. So over here on the left-hand side is some data on the PFAS constituents that are present in the solution. So for our purposes, total PFAS in this case is 40 analytes that are on the draft method 1633 list, plus any unidentified PFCA, perfluorocarboxylic acid precursor compounds that were picked up with total oxidizable precursor or top assay. So that's what that total PFAS number means. So for this groundwater sample, we started with 372 part per billion of total PFAS, and over the course of treatment, degraded by over 92%. The 6 compounds I've pulled out here are the 6 that are on EPA's new MCL list, because those are the ones that a lot of people are paying the most attention to at the moment. So just to give you some ideas there, for PFOA, we degraded that in the sample by 97%, PFOS, 3 orders of magnitude degradation, PFH excess, a little over 98%. And then this last number here is the sum of all those EPA MCL list PFAS masses, and that was degraded by over 99%. So on the right-hand side is our fluorine mass balance. So we're trying to show that the fluoride that we release corresponds to the decrease in fluorine that was originally bound to PFAS. And the way this plot is laid out is these colored bar plots are the fluorine mass fractions from each individual PFAS compound, plus a grouping of those unidentified PFCA precursors. And on the at the treatment end, what I'm showing is a big empty bar here for the fluorine decrease, so the amount of fluorine mass that was no longer detected at the end of treatment. Plus, in all of the samples, there was a small amount of PFAS that absorbed to the walls of a reactor. So we rinsed the reactor after the treatment to get a sense for how much was being absorbed. The black line is our fluoride release. So that's that ion selective electrode measurement that we're taking in real time during the course of the reaction. And we're getting pretty decent mass balance here. It's not perfect. So ideally, this black dot at the end of the treatment would line up with the top of that fluorine decrease bar. And we're in pretty good agreement here. I think that differences here could come from some fluorine losses in or fluoride losses in a reactor or something along those lines. But generally speaking, that real-time measurement that we're taking is corresponding very nicely with the PFAS degradation that we're measuring. This second sample is a groundwater foam fractionate. So the groundwater, the PFAS in the groundwater was concentrated with foam fractionation. So you can see compared to the previous sample, this is a much higher PFAS concentration. So we're starting with 31,500 part per billion total PFAS, which we degraded by about 95%. PFOA and PFOS in this sample both went to non-detect levels. So I put, greater than 99.9% here because I think 100% sounds a little too good to be true sometimes. Then PFH excess, we degraded that by almost 99%. And so then the sum of all those MCL list PFAS was over 99% degraded. So again, with the fluorine mass balance, for this sample, it looks pretty excellent. So this sample had a major mass fraction of PFOS, followed by unidentified PFCA precursors, 6,2,4-telomer sulfonate, PFH excess, and then PFOA. And our fluoride release corresponds very nicely with that decrease in fluorine. And I think with this sample, it's a little bit more apparent that we're degrading sort of a broad range of PFAS compounds. So you can see that the PFOS, PFOA, fluorotomer sulfonates, and even the PFCA precursors are all being broken down during the process, and we can account for that fluorine mass. This last sample is firefighting truck rinse water. So these are trucks that had been using AFFF in their pipes, and they're trying to wash all that out and replace it with PFAS-free firefighting foams. So in doing that, this is like the first water wash through the system. And so they rinsed the system out and collected the water, and in this case collected 58,200 parts per billion, a total PFAS concentration. So it's pretty good amount there. We saw a decrease of over 89% for that sample when we treated it. PFOS was a huge mass fraction in this sample, which we saw a decrease of over 99%. Then PFH excess, almost 82% decrease. PFBS, there was some of that in there. We did not really see a change over the course of this treatment time. The shorter chain compounds do take longer for us to break down. So likely if we had extended the treatment time, we would see degradation in that as well. Overall, the total MCL less PFAS, we saw a 95% degradation. Fluorine mass balance, the PFCA precursors was a very significant mass fraction in this sample, followed by PFOS and then PFH excess, and this is pretty typical for AFFF rinsate samples. Our fluoride release and mass balance doesn't look great, to be honest. So it looks like our fluoride release measurements were sort of over predicting the amount of fluorine decrease. And I think this kind of comes down to, this is just a hard sample for the analytics. So the analytical lab doesn't really like it when we send AFFF rinsates to them, to be honest. So it was a difficult sample to analyze. And also you can see compared to the other samples, this one had a significant amount of absorbed fluorine on the walls of the reactor. So we were struggling with that there. But generally speaking, that fluoride release was an indicator of PFAS degradation. So just some quick summary and conclusions. We're seeing efficient defluorination by the micelle accelerated PRD reaction in a variety of different water samples and over a range of initial PFAS concentrations. The total PFAS degradation for these samples range between 90 and 95%. Degradation of those EPA, MCL-less PFAS, so the sum of those 6 compounds range from 95 to over 99%. And generally speaking, we're getting good fluorine mass balance, and that has been a good indicator of reaction progress for us. What's next for Enspired Solutions? So I mentioned that this is a scalable solution, and this is our commercial scale piece of equipment. It is called the PFASigator. We are just finished commissioning this guy, and we have plans to do some field pilot testing in the very near future. Finally, I'll show you the leadership team here. And, thanks to them, but mostly thanks to our advising and funding organizations, particularly ESTCP, and a variety of small business related organizations in the state of Michigan that help us out as we are growing this thing. And with that, I will take questions if I have time.